All right, guys. So the OWL homework asks you to calculate brand new equilibrium compositions once an equilibrium has been reestablished. Meaning we had a system, it was fine, it was happy, and then we stressed it in some way. And so we're going to end up with new equilibrium concentrations. And so this problem here asks us to do that. Take a minute to pause the video, read the question, and make sure that your K sets up the same way as my K. All right, so let's see what's happening as we read the question. So it says that we have an equilibrium mixture right now, meaning that we have already allowed the system to come to equilibrium once. The question states that we have 0.215 molar PCl5, 5.08 times 10 to the minus 2 molar PCl3, and 5.08 times 10 to the minus 2 molar Cl2. Now this is at equilibrium the first time. I know that because it says equilibrium mixture. If you wanted to double check that it was at equilibrium, plug this line of numbers into this K expression, and you should get the value given to you in the problem. All right. So it wants to know what the new concentrations are once equilibrium has been reestablished, assuming that we add a little bit of one of the products. Now this is in moles and this is in molarity, but that's okay because we are in a 1 liter flask. So in this case, the molarity is the same as the number of moles. So I'll go ahead and write that in there just so you know. Now we're adding some of one of the products. So we're adding some PCl3. And assuming I wrote it down correctly, that's the amount that we are adding. Now we're not adding anything else. The question doesn't give us any numbers for anything else. The only thing we're adding is the PCl3. So that's okay for now. So I just added that. And right after the addition, so we'll call this just after addition. Right after the addition of that, we have the sum of these two values, which happens to be 8.67 times 10 to the minus 2. I'm going to drop my units now just to make things clearer. Now we didn't add any Cl2, so we still have 5.08 times 10 to the minus 2. We didn't add any PCl5, so we still have 0.215. So right now, this is just after the addition. And I want to know what the concentrations are once this system here reaches equilibrium, which means that I can take this just after addition and I can change it to I. All right, now we have our new initial quantity, because remember that's what I stands for in our ICE table. We were at equilibrium, but then we stressed our system. And so now we essentially have a new system, which is going to have its own ICE tables. So we know the initial. We know that because we added some of this. We didn't add any of those other ones. And so that's how we came out with these moles or molarity values here. What we need to know now is the change. And we can do this one of two ways. Either one would be valid in this case. Qualitatively, we added some of one of the product. We added some PCl3. So now, if we think in terms of the K expression, we have too much of this, which means we are going to consume some of those products and we are going to shift left because we need to make more reactants. If we make more reactants, that means that those reactants are going to have the positive value for the X because we are making more of them. We can't subtract and come out with more. If we wanted to do this quantitatively, we could confirm our qualitative assumption. So we can solve for Q, remembering Q is a number. It is set up the same way that K is set up, so we can use this expression. So my concentration for PCl3 is 8.67 times 10 to the minus 2 For Cl2, it's 5.08 times 10 to the minus 2. And for PCl5, it's 0.215. I do all of that, and I get a value of Q, of 2.05 times 10 to the minus 2, which happens to be bigger than K, which means that I have too many things in my numerator, which we decided up there, and that I need to make more reactants. So we've now figured out not once, but twice, that this side should be plus X, because we need to make more reactants. PCl5 is the only reactant, so it's the only thing that should have a plus sign. Both of your products, then, are going to get minus signs. Now, this should make sense because we added some product, and we're going to have to consume that product, which means it's going to go away. When you're setting up ice tables, the plus signs are going to be all on the same side, and the minus signs are going to be all on the other side. Since PCl3 has a minus X, Cl2 therefore has to have a minus X. We cannot mix the X's on the same side. So both of our products are going to have a minus X, and our reactant is going to have a plus X. So now we have made it to the point of our equilibrium line. We know what we had initially just after the stress. We know what the change should be in terms of sign. And so at equilibrium, we're going to have what we started with plus that change for the reactants. And then for the products, we're going to have what we started with minus that change. So now we have our equilibrium line. Now we're in a place where it looks kind of like what we saw in the exam. Now I'm going to make a completely separate video that's going to show you the detail in terms of solving out the algebra. Not everybody needs that, so I'm just going to set up K, go straight to the roots for now. I'm going to move down here to set up the K, because I want to be able to have room under that ice table to do my last step. So just to rewrite it, here is my equilibrium product constant expression, right? There's my equilibrium expression. Products over reactants, 1 mole of each. So everything's raised to the first power. If I take my equilibrium line in my ice table, my E line, and I plug my values in, my value for K should look something like this. And you set all that equal to the value of K, which is given to you in the problem, which is 1.20 times 10 to the minus 2. Now this number here is too close to 1 to be able to drop all of these x's. So that assumption that we talked about before the exam where we could drop the x doesn't work here, and you have to use the quadratic equation. Again, I'll detail the algebra in a separate video, so those of you that can get it on your own can just go on with your life. Now when you solve for the quadratic equation, you're going to get a positive root and a negative root. And in this case, those roots are 1.4 times 10 to the minus 2, or 0.136. Now remember what the root has to do. The root is equal to x, which means it's equal to our change. If I plug this one in, and I subtract 1.36 from 8.6 times 10 to the minus 2, I get a negative value. And that can't be, because I cannot destroy matter, right? We can't have a negative concentration. So this must be the root that makes sense. Okay? This is my value of x, and that x is equal to the change. All right, now I know my change. I'm going to go back up because I'm not quite done. My equilibrium right now is in terms of equations, right? I have a variable in each of my equilibrium concentrations. So what I want to do is actually use the change that I just solved for down here, 1.34 times 10 to the minus 2. And I want to solve for an actual concentration now. In this case, I'm adding x, so I'm going to add 1.34 times 10 to the minus 2. That addition gives me 0.2284. Here, I am losing x. X is going away, so I need to subtract 1.34 times 10 to the minus 2. And here I get 0.0733. And then here, I'm taking 5.8 times 10 to the minus 2. This is again a product, and my products have to have the same sign on x. All of those are molarities. These values here are what should go in your answer box in OWL. If you wanted to double check yourself, plug these numbers back into the equilibrium expression, right? 0.073, 0.0374, and 0.2284. You should come out with the same number that was given to you in the problem. Because even though we have different compositions at equilibrium between the second time we're at equilibrium, that's what you just solved for, and the first time we were at equilibrium, those are the numbers that were given to you in the problem, right? Those aren't the same concentrations, but the ratio of products to reactants should be the same between both of the equilibriums. So in both cases, we should come out with a K of 1.2 times 10 to the minus 2.